So in these next lectures, I will speak about Markov chains, Monte Carlo methods. So in order to explain what we will do, I will present an example, and for that I need to define graphs. So a graph will be G, will be a couple, V, which is a set of vertices, and E, a set of edges. So V will be a finite set, and E will be a family of pairs, so X, Y, such that X and Y belongs to E, to V, X different from Y. So V is a finite set. The elements of V will be represented by X, Y, and Z. And then we have the set of edges. So these are pairs. They are not ordered. And I'm simply telling you which pairs of the set V of vertices are connected. So you have here an example in which V is the set 0, set 7 square, and the set of edges will be just the pairs, all the X, Y, where X and Y belong to V, and the distance between X and Y it's equal to 1. So we have here the representation of this graph G, and this is an example of graph. So now that we defined a graph, I want to introduce what's called the hardcore model. So we start from a graph, G, which is VE, and here is an example. And now we will place particles at sides of V. So the state space, which I will represent by omega, will be a subset of 0, 1 to the power V. Elements of omega will be represented by Greek letters eta and xi. So eta x for x in V will be either 0, 1. 1 if there is a particle at site x for eta, for the configuration eta, and 0 otherwise. But I want to introduce a hardcore interaction between these particles. And so omega, so what I will do is that I will not allow two particles to be sitting in sites which are connected by an edge. So my state space omega will be the elements of 0, 1 to the power V, but the elements such that you don't have two particles sitting on sites which are connected by an edge. So this means these are all etas such that eta x, eta y, it's equal to 0 for all edges, which means for all x, y, which belongs to the edge set E. So this is my state space, and here is an example of an element of that space. So assume that the graph is given by this figure, and therefore we can start to place particles on this graph. But once we place a particle on a site x, all its neighbor sites, so the sites which are connected to x by an edge, are points in which I'm forbidden to put a particle. So this is a configuration, an allowed configuration, and this is a configuration which doesn't belong to omega because you have two particles which are connected by an edge. So this is my state space, and this is called the hardcore model because, well, it's representing a gas which has a hardcore interaction in the sense that if you have a molecule of this gas at one point, then all neighboring sites are forbidden to have particles. So this is a model. So now let me introduce a measure in omega. So let me represent by the absolute value of omega the number of elements. So this is the number of elements of omega. And let me define a measure pi on omega, which to a configuration gives a measure which is equal to 1 over the total number of configurations. Of course, the problem here is that it's very difficult to compute the total number of configurations of a graph, unless the graph is a very small graph. Otherwise, it is very complicated to compute exactly the total number of configurations. Therefore, well, this measure, it's a very simple measure. It's the uniform measure of all configurations. The problem is that we can't access really what is the value of omega. And the problem which I want to address in this lecture is the following. Well, I give you a computer, and this computer is able to create a sequence of IID random variables. So U1, U2, UN, it's a sequence of IID random variables, and these random variables, Uj, are distributed according to a uniform 0-1 distribution. So this you are given this sequence of IID, and what I want you is to give a sequence of configurations whose distribution is given by this measure pi. So I want you from this sequence of random variables, which, well, your computer is able to create random numbers, and from these random numbers you have a reasonable approximation of a uniform distribution. So I'm assuming that you're giving these sequence of IID random variables which are uniformly distributed in the interval 0-1. So I assume that you have that. And now I want you to construct from this sequence of random variables a sequence of configurations. So a configuration 1, a configuration 2, and I want this configuration to be distributed, to be independent, and to be distributed according to this measure pi. Let me solve this problem in a very simple setting. So assume that I want you to, starting from this sequence, to provide a sequence of numbers, x1, x2, and so on, which are IID, and such that the distribution of xj, it's uniform over the set of digits 0, 1, up to 9. So what would you do? Well, it's very simple. You would define a function phi from 0, 1 to 0, 1, 2, up to n. This function would be, for example, given by, well, between 0 and 1 over 10. Let's say that closed at 0 and closed at 1 over 10, this function will be equal to 0. Then from 1 over 10 to 2 over 10, you would define this, let's say, closed at 2 over 10 and open at 1 over 10. This function will be equal to 1, and you will do that up to 1, closed at 1 and open at 9 over 10. This function phi will be equal to 9. And so if you define xj to be phi of uj, you have, from this sequence of IID random variables, created a new sequence which is IID and whose distribution is uniform in the points 0, 1, up to 9. Now, I want you to do it. Well, what we are planning to do is to provide a method in which you are able to, given this graph, given this hard-coded model, create a sequence of configurations which are extracted from this measure. So this sequence will be independent, and the distribution, so that will be a sample, what's called a sample, of this measure. So each random variable will be distributed according to this measure. Each configuration will be distributed according to this measure. So this is the plan. Create a method, an algorithm, which allows you to simulate this measure, which means to extract, to create random variables which are distributed according to this measure. And the problem here is that we don't have access to this number. We don't know how many configurations there are. And so we cannot repeat what I proposed here since the total number of elements is unknown. So this is what I will present in these next lectures. So let me give you now a second example, which is called the Q coloring model. So now you fix Q larger than 2, and you have again a graph, G, which is V, E. And what you'll do is that, well, you interpret this Q as a certain number of colors. So you want to put a color to each point of your set V, but in such a way that if you choose 2 points which are connected to by an edge, these 2 points have to have different colors. So my state space will be a subset of all possible colorings, and all possible colorings is the set 1q to the power v. So to each point of v you associate a color, which can be 1, 2, or q. But now, so this is a subset, but now you want to impose that if 2 vertices are connected by an edge, well, then the 2 colors have to be different. So the color of this point has to be different from the color of these 4 points. So the state space will be, again, I will represent by eta the elements of our state space, omega. So now eta x will be an element of the set 1q. This is the color of the site x for the configuration eta. And my state space will be all etas which belong to the set 1q to the power v, but with the restriction that eta x, it's different from eta y for all edges. So for all xy which belongs to the edge set. And now, well, there is a problem. The problem is that, well, you don't know if it's possible to give a coloring of this graph, let's say with 2 or 3 colors, right? So let me give you an example. Maybe the set omega is just the empty set. So let's consider a simple example. Let's assume that our graph is this triangle and that you are given Q only 2 colors. So it's clear that it's not possible to color this graph satisfying this condition because, well, if you put a color to this vertex, let's say color 1, then this one has to be different, but there are only 2 colors. So I'll take color 2, and then at this point, you cannot use color 1 nor color 2, so this set is actually empty. If the graph is this graph which I just draw, and if you take Q equal to 2, then it's not possible to color this graph only with 2 colors. So there is a famous theorem, which is the 4-color theorem, which tells you that if G is a planar graph, and planar here means that the set V is contained in R2, and that this graph has no edges which cross. So if you have, say, these points, and these points are connected by an edge, then this is not allowed because, well, these 2 edges. So if this happens for your graph, you say that, well, this graph, it's not planar. So by assuming that the graph is planar, then it is known that you can color your graph with 4 or more colors. So there is an a priori problem, but I will assume here that Q is sufficiently large for this set to be different from the empty set. So I'm assuming that omega is different from 0, and now, again, I will define a measure on this set, which is the uniform measure. So I'm giving weight to each configuration equal to 1 over the total number of configurations. And my problem is, again, to create a sequence, a sample of this measure. So a sequence of configurations which are independent and whose individual value are distributed according to this measure. And here again, it's very difficult to compute the total number of configurations, so there is no simple way in which we can obtain such a sequence. And what I will present next is a general strategy in order to solve this problem, in order to extract samples of this measure by using Markov chains. So I hope you understood the problem. You have a sequence U1, U2, and so on of id random variables. Uj is distributed according to a uniform 0, 1 distribution. And let's say I give you a graph with n by n, and n it's quite large, let's say 100. I give you, so the set of vertices will be 1n square. Then I give you a certain number, let's say q equal to 4 colors, and I want you to create sample, or to create a coloring, and to claim that this coloring you created, so that the algorithm you proposed, provides a sample, so a configuration, which is distributed according to the measure pi of eta, which is equal to 1 over the total number of sides. So how from this sequence create a configuration and whose distribution is given by this measure. So this is the problem. And so now let me propose a strategy. And this is the Markov chain Monte Carlo strategy. So the strategy is the following. What I will do is I will create a sequence xn which is a Markov chain. With these random variables uj, I will create a Markov chain. This is a discrete time Markov chain. And this Markov chain will, the state space of this Markov chain will be the set omega. I will represent by p eta psi, the transition probability of this Markov chain. So this is the probability that the Markov chain jumps from eta to psi. This Markov chain is homogeneous, will be homogeneous, and it will be irreducible and aperiodic. Now, since it's irreducible and aperiodic, what I know is that if I start from any configuration eta, and I let this Markov chain evolve up to time n, so xn will represent the state of the Markov chain at time n, well, I know that the probability that the state at time n is equal to psi, as n converge to infinity, that this converge to the invariant measure of this Markov chain. So I know that since this Markov chain is irreducible and aperiodic, and the state space is finite, there exists a unique stationary state. Let me represent it by mu. And, an important theorem in the theory of Markov chains tells me that the process is ergodic, which means that if I start from any configuration eta, I let the process evolve, the distribution at time n, it's converging to the stationary distribution mu, which means that the state, the probability that it is at psi at time n, it's converging to mu of psi. So the idea is to construct a Markov chain which is irreducible and aperiodic and whose stationary state, mu, it's equal to the measure we wish to simulate, so pi. If I can do that, so if I can create this Markov chain, I can start from any configuration. I run this Markov chain by using these uniform random variables. So I create this sequence by, and I will show you how to do that with these uniform distributions. I run it, I let time evolve, I take a very large time n, and what I know is that this distribution, it will be very close to the stationary distribution, which is pi. Therefore, xn, the distribution of xn will be very close to pi, and therefore, well, this is a way in which I can produce a sample from pi. So the problem will be to construct these Markov chain. So given graph, given a state of configurations omega, how to construct such a process whose invariant, well, which is irreducible, aperiodic, and whose stationary state is pi. So this is what I'm going to present in next minutes. So in order to give you a precise idea, let me go back to the hardcore model. And in this hardcore model, I want to define a Markov chain which is aperiodic, irreducible, and whose invariant measure is the uniform measure. So remember, in the hardcore model, we have a graph which is formed by vertices and edges, and we defined omega to be the configurations of 0, 1 to the power v, such that, well, if you take any two sides which are linked by an edge, they are not occupied at the same time. So this means that eta x, eta y equal to 0 for all y which is a neighbor of x. So mind that here I'm introducing a new notation. So I will say that y is a neighbor of x if xy is an edge. So if xy belongs to the set of edges. And so let me make a picture which I will use to illustrate what I'm proposing. So I'll propose an algorithm, let me write it here, to construct this Markov chain. So the idea is that at some point you have a configuration. So let me illustrate this configuration here. It has, say, 3 particles. And so the algorithm works as follows. You choose at random a vertex. So saying that I'm choosing at random means that I choose this vertex with uniform probability. So there are v sides. I take one of them with probability 1 of v. Then say that you chose this side. Well, two things may happen. Either I'm allowed to place a particle on this side, or I'm not. So if I'm not allowed, I can't do anything, so I don't do anything, while if I'm allowed, I will flip this side with probability 1/2. So let me be clear of what I'm doing. For that I need some notation. So if x is a vertex, let me represent by sigma x of eta a new configuration. So eta is a configuration, sigma x of eta is a new configuration. Its value at y, it's equal to eta y, if y is different from x, and it's equal to 1 minus eta x if y is equal to x. So this means that I'm flipping the configuration at x. Mind that if eta at x is equal to 1, this means that for this new configuration at x, it is equal to 1 minus 1, 0. While if it's equal to 0, it becomes 1. So and for the other configurations, I'm not changing anything. So this is new. So here, and now let me define those sites at which I'm able to change. So let me define a set V of eta. So I fix a configuration eta, and I'm representing by V of eta all sites which are in which I'm allowed to flip the particle, or which I'm allowed to place a particle. So this is all y's in V, such that eta 0 it's equal to 0, eta z it's equal to 0 for all z which are neighbors of y. So y belongs to this set if all neighbors of y are equal to 0. So let's go back to this example. And let's see what are, maybe let me put some more particles. So let's say that this is the configuration, and now I want to, so in orange I illustrated the configuration eta, and now I want to define this set V of eta. So these are all points in which all neighbors are equal to 0. So this is a point which belongs to V because the two neighbors are equal to 0. That one doesn't belong, so let me place an X. This one doesn't belong because this site is occupied. This one does not belong, this one does not belong, but this one belongs. This one does not belong, this one does not belong because this one is occupied, this one does not belong, this one does not, this one belongs. This one doesn't, this one doesn't, this one doesn't, this one belongs to my set. This one doesn't, this one belongs. 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 This one belongs. This one doesn't. This one belongs. This one belongs. This one belongs. This one doesn't. This one belongs. This one doesn't. This one doesn't. And this one belongs. So in purple, you have your set V of eta. So what I claim is that, well, if X does not belong to V of eta, so if X is not in purple, you do nothing. You do nothing, well, because if X does not belong to this set, this means that there is one neighbor which is 1, and so there is nothing you can do at X. It has to be 0, because otherwise you escape from your set omega. But if now X belongs to this set, so if you're allowed to change the value, if X, eta X can be 0 and can be 1, what you do is that with probability 1/2, you change the spin. So you move to eta sigma x eta. And with probability 1/2, you stay where you are, so you keep eta. So let me repeat what is the algorithm I'm proposing in order to construct this Markov chain. Keep in mind the definition of this set. So these are the sets of points in which I can place a particle at X for the configuration eta. So I first choose at random a site X. So with probability 1/V, I just pick a site. So I pick that site. Now, if that's the site I chose does not belong to V, there is nothing I can do. So I keep the configuration. So I don't change the configuration, so I keep the configuration to be eta. But if X belongs to this set v of eta. With probability 1/2, I flip the value at x of the configuration eta. So I replace eta by sigma x of eta. And with probability 1/2, I keep the configuration eta. So that gives me an algorithm. And now, I need to translate this algorithm in terms of a probability transition. So to define a Markov chain, a discrete time Markov chain, I have to tell you what is the probability that I will jump from eta to psi. And I will just translate this algorithm in terms of this probability. The first thing I observe is that I never change the configuration in more than one site. I never change simultaneously 2 sites or 3 sites. I jump from eta, either I keep eta or I change eta at one site. So let me define the distance between eta and psi. So this distance will be just to compute the number of sites at which eta and psi are different. So this means that I just sum over all sides, and I sum 1 each time eta x is different from psi x. So that this distance can be equal to 0 if psi is equal to eta up to v. It's a number between 0 and the total number of sites. Well, what I claim is that this probability is equal to 0 if the distance between eta and psi is larger or equal to 2. Now, if eta and psi, this distance is equal to 1, this means that eta and if the distance between eta and psi is equal to 1, this means that psi it's equal to eta on all sides but 1. So let me call x the site at which they are different. And this means that, well, since the distance is 1 and eta x only takes 2 values, either 0 or 1, this means that psi is equal to sigma x eta for some x. So that there exists x in V such that psi is equal to sigma x. So if I want to define this probability, well, I defined it for if the distance is larger or equal to 2. So now let's define when the distance is equal to 1. But when the distance is equal to 1, this means that psi is equal to sigma x eta. So I have only to tell you what is the probability that eta jumps to sigma x of eta. So what is this probability? Well, when do I jump from eta to sigma x eta? Well, I have to go back to my algorithm. This means first that I chose x. So this happens with probability 1 over v. And, well, this means also that x belongs to v of eta. Because otherwise, this probability is 0. So if x does not belong to v of eta, this probability is 0. But if x belongs to v of eta, the probability that I change, it's 1 over 2. So this is the probability that I jump from eta to sigma x eta. It's 1 over 2 multiplying v, the total number of sides, if x belongs to v of eta. If x does not belong to v of eta, this probability is 0. So let me repeat. I'm defining this probability for all, I'm fixing eta, and I'm defining this transition probability for all psi. I first consider the case in which the distance between eta and psi is larger or equal to 2, and this I'm saying it's equal to 0. Now I'm considering the configuration psi for which eta and psi, the distance is equal to 1. If the distance is equal to 1, this means that psi is equal to sigma x eta for some x in V. Well, this x either belongs to V of eta or doesn't belong. If it doesn't belong, this transition probability is 0. If it belongs, it's equal to 1 over 2V. Why 1 over 2V? Because first, if I want to jump from eta to sigma x eta, I have to choose x, and this happens with probability 1 over V, and then I have to flip and to flip, and the flipping probability is 1 over alpha, 1 over 2. So this is the probability. So this takes into account all possibilities in which the distance is 1. Because if the distance is 1, this means that psi is equal to sigma x for some x, and I have to consider these two cases. And now finally, so this is this probability, this is the case in which the distance is 1, and finally, the probability that you remain where you are, it's 1 minus the probability that you jumped, but the probability that you jump, it's 1 minus the sum over all x in V, but not all x in V, all x in V of eta, because it's 0 otherwise, 1 over 2V. So if I want to see what is the probability that you jump, you have to sum these p eta psi for all psi different from eta. If the distance is larger than 2, it's 0. Now let's see if the distance is 1. If the distance is 1, well, what is the, you have to sum all these probabilities, so you have to sum this quantity for all configurations. But what are all configurations you can obtain? Well, these are all configurations in which you flip one of these purple sides, which is what I'm summing here. And what is the probability I have to sum? This is 1 over 2V. So this is equal to 1 minus V of eta divided by 2V. And in conclusion, so let me write it here. So in conclusion, I have the following. The probability that you jump from eta to sigma x of eta, it's equal to 1 over 2V if x belongs to V of eta, and it's equal to 1 minus V of eta, sorry, let me write it in this way. The probability that you jump from eta to psi, it's equal to 1 over 2V if psi it's equal to sigma x eta, and x belongs to V of eta. It's 1 minus V of eta divided by 2V if psi it's equal to eta, and it's 0 otherwise. So this is the conclusion at which we've reached by analyzing this algorithm. You jump only for two different types of configuration, either to a configuration sigma x eta if you are allowed to jump, so if x belongs to V eta, and this happens with this probability, or you stay where you are with 1 minus this probability, and all the other jumps are forbidden. So mind that if I sum over psi, what I get is 1, because by summing this expression, I get exactly this one, so they will cancel, and 1 will remain. And mind also that this probability is strictly positive because mind that v of eta it's larger or equal to 1 if there is a particle because if there is a particle, so there is a particle at some point, this particle is connected to other points, and this means that at these points the jumps will be forbidden. Of course, something I didn't say, but I will always assume, is that the graph is connected, so that it's always possible to mind observation. So I'm always assuming, I didn't say it, that the graph is connected. So that you can go from any point to any point on your graph by edges. So there is always a path from any two vertices following the edges. So that's very important. So I know that if I have a particle on one side, so there is at least one edge arriving at that vertex, because if there were no edges, this graph will mean not connected, because I couldn't connect this to another vertex. So there is at least one edge. And if I take the point at the end of this edge, this point does not belong to v of eta, because there is a particle at this point x. So this means that this probability of staying at your configuration, it's always strictly positive if there is at least one particle in the configuration. So this is the definition of the transition probability, and now what I claim, and this is what I will prove next, is that this transition probability is irreducible, it's invariant, and that the stationary state of this transition probability is the uniform measure. So I left here the transition probability of the Markov chain I just defined, and now I claim, as I said, that this Markov chain is irreducible, it's aperiodic, and that the uniform measure pi of eta, it's a stationary state, is the stationary state. So let's prove all these properties. That it's aperiodic, it's clear, because the probability that you jump from eta to eta, it's strictly positive, right? Because v of eta divided by v, that this is, well, this is the total number of sides which a jump is allowed. This is, of course, less than the total number of sides, so this is less than 1, and therefore this probability is actually larger than 1/2, and which means that since you're allowed to jump from eta to eta, from any configuration to any configuration, this means that the chain is aperiodic. So this is easy. Now let me show that it's irreducible. Well, to show that it's irreducible, I have to show that I'm always, if I take two configurations, eta and psi, I have to construct a path, say eta 1 up to eta m, such that the probability that I can jump from the configuration eta j to eta j plus 1, it's strictly positive. This for j between 0 and m, and here I'm taking eta 0 to be eta, and eta m plus 1 to be psi. Right? So I have to construct a path going from eta to psi, and a path in which the probability that I can jump from eta j to eta j plus 1 is always strictly positive. So in the hard-code model, that's very easy. So assume that you start with some configuration eta, which is here, and you wish to go to some configuration psi, which is something else. So that's very easy to do. And what you do is that, well, you start from eta, and what you can always do is to erase a particle. So I can construct a path from this configuration to the empty configuration. So the configuration in which there is no particle, just by suppressing the particles one by one. So first I remove, the first step I remove that one, then I remove this one, that one, that one, that one, and after a number of steps which is equal to the number of particles, I reach this configuration. And I can do the same thing from that configuration to this empty configuration, and now I can just reverse this path to go from the empty configuration to that configuration by adding one by one all these particles. So that creates a path. Now I have to check just that I'm allowed to jump, but from one configuration to the other. But that's clear because if I have here a particle, this means that all the neighbors are empty. So this means that this site X belongs to the set V of eta, and therefore the probability that I go from this configuration to the same one in which I removed that particle is just 1 over 2V. And this same reasoning applies to all particles. And here again, well, I can create, let's say that I started from 0, and now I create this first particle. Well, since this configuration is an allowed configuration, it means that all neighbors of this point are empty, which means that this point belongs certainly to the set V, and therefore I'm allowed to jump from the empty configuration to that one, and the same argument applies to all the others. So it's clear that these probabilities are all equal to 1 over 2V, and therefore that this chain is also irreducible. So we proved that the chain is irreducible, it is aperiodic, and what we really need to show is that this chain has the stationary state of this chain is the uniform measure. And for that, I will prove that actually it is reversible. So this is the important word here, reversible. So remember that a state is called reversible if it satisfies the detailed balance condition. So the detailed balance condition is that the probability that I start from eta and I jump from eta to psi, that this is equal to psi pi of psi times the probability that I jump from psi to eta. So I claim, I have two claims. I claim that, well, first, if this identity holds, and this is called the detailed balance conditions, so I claim that if the detailed balance conditions hold for all eta psi, then the measure pi is invariant, and I also claim that actually the uniform measure satisfies these identities, the detailed balance condition for this transition probability. So first, let me check that detailed balance imply that pi is stationary. So this is a general statement on Markov chains. So if I want to show that mu it's a stationary state for discrete time Markov chain, I have to show that mu p it's equal to mu p, which means that for all eta, mu p of eta it's equal to mu of eta. But what is mu p of eta? This is the sum over all psi of mu psi p psi eta. So this is the left-hand side. Now let me use this detailed balance condition to replace mu psi p psi eta by mu eta pi p eta psi. So this is equal of mu of eta p eta psi. Now by summing psi, I get 1. So this is equal to mu of eta. And this is exactly what I wanted to prove, right? I proved that mu p is equal to mu of eta for all eta. So indeed, these conditions are stronger than stationarity. They imply stationarity. So this is the first claim. And then my second claim is that the uniform measure is reversible for this transition. So uniform measure, since pi is the uniform measure, pi of eta is equal to pi of psi. And what I need to show is that p of eta psi is equal to p of psi eta. So if I want to prove that, first, if the distance between eta and psi is larger or equal to 2, this means that this probability is 0, that probability is 0, and therefore this identity holds. Now, if the distance between eta and psi is equal to 0, this is also true because, well, if the distance is 0, this means that psi is equal to eta, and this is trivially true if psi is equal to eta. So the only important case is the case in which this distance is equal to 1. If this distance is equal to 1, well, then if the distance is equal to 1, this means that psi is equal to some sigma x eta. And x has to belong to v of eta. Because, mind, this distance is equal to 1, so this means that psi is different from eta, so they differ from eta. And so they differ at one side, so there exists an x in v at which they differ. And, well, since they differ and both are elements of omega, this means that all neighbors have to be equal to 0, have to be empty, right? Because let's say that if for the configuration eta, the site x, it's empty, this means that the site x, it's occupied by a particle for the configuration eta. And since psi, here I have to prove that this identity holds for all configurations of the set omega, well, if psi belongs to omega, this means that all these four sites, all neighbors, are empty. So this means, in particular, that x belongs to v of eta. And also, if psi is equal to sigma x eta, this also means that eta is equal to sigma x of psi. Right? The eta and psi differ at only one side. So one at the site x is 0, the other one is 1. So I get one from the other just by flipping what's happening at x. So not only psi is equal to sigma x of eta, but eta is also equal to sigma x of psi. So, and also, x also belongs to v of psi. Because since psi and eta coincide on all the sides, this means that, well, these sides are, if they are empty for eta, they are also empty for psi. And if they are empty for psi, they are empty for eta. But then, by definition of our transition probability, this means that p of eta psi, which is p of eta sigma x of eta, this is equal to 1 over 2 divided by v. And p xi eta, it's equal to p xi sigma x of psi, and this is also 1 over 2v. And this is 1 over 2v because x belongs both to v eta and to v psi. So we have computed these two probabilities, and indeed they are equal. So this shows that indeed p of eta psi is equal to p of psi eta, and therefore that this relation holds for all eta and psi in omega, because all the other cases are trivially true. Therefore, we proved that indeed this Markov chain we just constructed have the three properties we need, which means now that I can start from any configuration, say the empty configuration, so start at time 0 with no particle, let the process evolve, and what you know, if we represent by xn the state of this Markov chain at time n, we know that this probability, that this is equal to psi, converge to psi psi. So if I want to simulate this probability, if I want to create a configuration whose distribution is close or it's equal to the distribution of pi, what I need to do is start at time 0 from an empty site. I run this Markov chain. I have to tell you how to run this Markov chain using uniform distributions, but that's easy. So you run your Markov chain up to a very large time, and the configuration by Theorem on Markov chain, the configuration you get at time n, the distribution of this configuration is very close to the uniform distribution. Of course, there are two problems here. The first problem is, well, how large has n to be? This theorem tells you just that you converge, but it doesn't tell you how large n has to be. So if we want really to use this strategy, what we will need to do is to get a bound on the distance between this distribution at time n and the stationary distribution, to say, well, that how fast does that decrease as n goes to infinity. So that's a very important problem. We need explicit bounds on n, so we'll have to say that if you take the supremum over all xi's here, well, we have to provide you how fast this decreases to 0. Is that as polynomial in n? Is this exponential in n? How fast this difference converges to 0? We know only, the theorem tells us only that it converges to 0. But now we need explicit bounds in n. So I'm sorry, here this n is that one. We need estimates to tell us how large we need to take n in order for this distribution to be close. And this is a second point. This distribution, it's equal to pi only asymptotically as n converges to infinity. If we stop at certain n, this distribution, it's not exactly, so there is an error. And this bound will tell us how large is the error we are making by taking psi through this algorithm and not pi. So how far is the distribution of psi of this random variable from the uniform measure? So there are two problems that we need to address. So it's the speed of convergence of this question and the fact that we are not getting exactly configuration distributed according to pi, but close to this distribution. And so this is one problem. There is a second problem which is very interesting, is that here I defined one Markov chain whose invariant measure is pi, and it's reversible. Of course, it's easy to create other dynamics, other Markov chains, which have the same invariant measure pi. And maybe one of them converge faster to the stationary state than the other. So we would like to investigate, and this is a very interesting topic, the rate of convergence to stationarity. Is there a certain type of dynamics which converge faster to the stationary state than others? Because that would be make the algorithm much more interesting. If you have an algorithm which converges faster, you will use that one instead of one which converges slower to the stationary state. So these are the problems I wish to address in these lectures. So actually, the algorithm I proposed, it's an example of what's called the Gibbs Sampler, which I will explain now. So the setup is the one we had. We have a set of edges and vertices which forms a graph. I'm always admitting that this graph is connected. The set of vertices is finite, And then we have a set, S, and S it's a finite set, so in our examples, S would be either 0, 1, so in the hard-coded model, or the number of colors. And we had omega, which is a subset of S to the power v. Now we have a measure, pi, which is defined on omega, so this is a probability measure. And we want to define a Markov chain, which is aperiodic, irreducible, and whose stationary state it's pi. Markov chain on the set omega. For this, what we did before, it's you first choose a site, and you do that uniformly over all possible sites, and then you update. So now I'm proposing a general strategy in which we will update a configuration, site by site. So for that, I will need a notation, so I will represent by pi eta x. So this is a probability measure on the sets S. So either 0, 1, or 1q, or your finite set on which you are working. And which is this probability? So this corresponds to what is the probability. So formally, this is, so let me call the points of S. So x, y are used to v, so S will be A, B, C, and so on. So these are the elements of S. They are represented by the letters A, B, and C. So pi x eta x of A will be the probability that under pi, under the measure pi, that eta x it's equal to A, given that, or maybe psi x it's equal to A. So here I'm fixing eta, it's an element of my set omega, x it's an element of V, and I'm defining a measure on S. And what is the measure of the point A? Well, this is the probability that I have a configuration psi, its value at x it's equal to A, given that the value of psi at y it's equal to eta y for y different from x. So this is the definition of this probability. So what does that mean? That means that pi eta x of A, it's equal to the probability of the configuration. So mind that the conditional probability is the probability of the intersection. So this is the probability of the configuration, which at x it's equal to A, and at y for y different from x it's equal to eta y. So I will represent this configuration by y eta ch x. So this is a new configuration. So let's say that if you have a configuration eta and a point x, eta x ch, it's the configuration which is defined. So this is a new configuration, and it's defined for all, so it's an element of S V minus x. So I'm removing from the side of vertices the point x, and I have, and on the other side, so this configuration eta x at side y, it's equal to eta y for y different from x. So this is just to represent, you have a configuration, you remove side x, so remains all side y different from x, and this is just the configuration you have. So this is a new configuration, but which is defined on all sides but x. And so this, now it's a new configuration, which on all sides different from x, it's equal to the value of eta, and at side x, it's equal to A. So this is the probability under pi of this configuration, and that I'm summing over all possible values. So B in the set S of pi B eta chech x. Okay, so I hope the notation is clear. So this is a new configuration of omega, which at x it's equal to b, and outside x it's equal to eta. And this is this probability which I just defined. If you give me a configuration on the side, so this is a probability on S, and it's given by this ratio. Mind that this ratio, if you sum over all A, you get 1. By summing over all A, these terms will cancel. So I will use this notation in order to define the Gibbs sampler. So the Gibbs sampler, it's as before, moves in 2 steps. You first choose a site X at random. And then once this site X is chosen, you replace eta by the configuration A eta x. So mind, here you're taking your configuration eta and you're changing the value of eta at x, putting the value A, and this with probability pi eta x of A. And that includes the case in which A is equal to eta x, right? In this case, that will give you just p eta x of eta x. Right? So this is the Gibbs sampler, and so I have 2 claims again. The first claim and more general claim is that this provides me an algorithm, a Markov chain, which is irreducible under certain conditions, aperiodic, and whose invariant probability measure is pi. And then that the previous algorithm corresponds exactly to this one. So what I will do now is I will first write a formula for p eta xi, as I did for the hardcore model. Then I will show that in the hardcode model, the algorithm we proposed corresponds to this Gibbs sampler. And finally, that this algorithm, that is this Markov chain, has the 3 properties needed. So I just wrote here the formula for this measure. And now let me first show that, let me obtain a formula for p. So I want p eta xi. And well, I first claim that if the distance between eta and xi, that this is equal to 0 if the distance between eta and xi is larger than 2, because you see that here in the algorithm I'm changing only a site at a time. Now let me take the case in which the distance between eta and xi is equal to 1. So that means that eta and xi are equal on all configurations but at 1 point. So let me call, so this means that eta, there exists x such that eta y is equal to xi y for all y different from x. And there exists a different from b such that eta it's equal to a. This means that eta x is equal to xi x, right? They are equal at all configurations. And this means that eta, well, there exists a different from b, since the distance is 1, such that eta is equal to a eta bar x, and xi it's equal to b eta bar x. Right, so what is now the probability? So what I need to examine is the probability that I jump from since in this case there exists this x, it's enough that I consider the case in which I'm jumping to b eta bar x. And what is this probability? Well, this probability, it's first I need to choose x, and this happens with probability 1 over v, and then I have to move from eta to this new configuration, and this happens with this probability. So this is 1 over v, and this is the probability that eta x b. And this is for x in for all x in v, and for all b in S. So this is, so maybe in order to have a simpler formula, let me represent by txa of eta the new configuration. So this is a new configuration omega, which at site y, it's equal to eta y for y different from x, and which is equal to a for y equal to x. So this is the a here. And so what this formula is telling me is that the probability that I jump from eta to tx a of eta, it's equal to 1 over v p eta x a. And this for x in v and for a in S. So this is the formula we have for this transition probability. So mind that, so here I just rewrote what we proved. So we obtained a formula for the probability that you jump from this configuration to that one. It's given by this formula. And it's, well, this probability, I wrote it in this way, but so this is the probability to jump from this configuration to this one. And we also proved that the probability that you jump from eta to psi, it's equal to 0 if the distance is equal to 0. So that takes into account all configurations psi which are at distance 1 from eta, because if psi is at distance 1 from eta, this means that they differ by 1. So this means that psi is equal to one of these configurations for some x and some a. And, well, and in this formula, it's hidden the probability that you jump from eta to eta. If you want the probability that you jump from eta to eta, you have to sum over all these, because you see, if you take a equal to eta x, then tx eta x of eta, it's eta. And so this gives you a positive probability that you jump from eta to eta. So if you want to compute the probability that you jump from eta to eta, what you have to do is to sum over all x in v, and then take the probability that you are jumping from eta to tx eta x of eta. So this is eta, so this is what I wrote here. And what is this probability? It's given by that. So this is equal to 1 over v, sum from x in v of the probability eta x of eta x. And now, if you want to go further, you can just replace p eta x by its value, and you'll get here that this is equal to 1 over v, sum x in v, and that gives you p a eta x, so that's p of eta, divided by the sum of b B in S of P B eta x. So this is the probability that you jump from eta to eta, and mind that this is strictly positive. The sum is strictly positive because, well, all these terms here are strictly positive, and it's of course bounded by 1 because all these terms are less equal to 1, so you're summing over v, dividing by v, so this is bounded by 1. So that tells you that it's strictly positive. In particular, this chain is aperiodic because you can jump from eta to eta with a positive probability. So, and that gives you an entire description of the transition probability, right? If the distance is larger than 2, then it's 0. If it's equal to 1, exactly equal to 1, then it's given by that. And here is the probability that you jump from eta to eta. Now, well, you have to prove that this chain is irreducible. And of course, that will depend on the model, on the space omega. Here you see that you are allowed to jump, but, and I will return to that. If you take, for instance, the Q-color model, well, it's not clear at all if Q is small that these dynamics, the Gibbs Sampler, it's irreducible. It can be a very hard problem to show that this model is irreducible. So you have to go model by model. Well, we have seen in the hard-code model that these algorithms produce irreducible dynamics, but for some examples, as the Q-color model, if Q is small, this can be a very difficult problem. So you have to face that problem model by model. And now, but what I claim, which is easy to prove, it's that the measure pi which we started from is stationary. Actually, it satisfies, so it's reversible. It satisfies the balance conditions. So let's prove that. We have, let me erase here, I don't need that formula again. So we have to show that pi of eta, p eta xi, that this is equal to pi xi p xi eta for all eta and xi in omega. That's fine. Now, so let's prove that. If d xi is equal to 2, these probability are equal to 0, so this is an identity. And if eta is equal to xi, this is also easy because, well, it's a tautology. Then we have to consider the important case. It's the case in which the distance between eta and xi is equal to 1. Well, if eta xi, the distance is 1, this means that they differ at one side. So there exists x in V such that they are all equal. They are equal on the other sides, and they are they differ on one side. So there exists an A different from B in S. We have seen that eta it's equal to A eta ch x, and xi it's equal to B eta ch x, which is also B xi ch x, and this is also equal to A xi ch x, right? Because eta ch x, so since eta and xi are equal at all sides different from x, these two configurations are equal, and therefore, well, eta, which is equal to that, it's also equal to that. So now I can write this identity. I have P of eta, then what is the probability that jump from eta to xi? Let's go here. Well, eta is this configuration, xi is this one. So xi, by our previous notation, it's equal to T x B of eta, right? Because psi, it's a deconfiguration which coincides with eta at sides different from x, and I'm sorry, this is not 1 minus x, this is a, right? And at side x, psi, it's equal to b. So psi is this configuration, and similarly, eta, it's equal to tx a psi. Then let me write p of eta, then the probability that you jump from eta to psi. But the probability that you jump from eta to psi, since psi it's txb eta, so this is the, so I'm considering the left-hand side. So the left-hand side, it's equal to p of eta times the probability that you jump from eta to txb of eta. And this is equal to p of eta. So now let's see here the probability. Well, the probability it's 1 over v, and then p eta x b. So this is p eta x b. But this is p of eta divided by v. And now let's write what is p eta x b. So this is p b eta ch x divided by the sum. Here I'm not allowed to use b, so c in s, p c eta ch x. And mind that the configuration which is at x equal to b and which is equal to eta ch outside x, this is psi. So this is equal to p eta p psi divided by v and divided by the sum over all c of p c ch x. And you see that if now I repeat the same thing on the right-hand side, I'll get exactly the same thing. P theta, pi psi divided by this quantity, right? Okay, maybe I'll do it, just make sure that you understand. So let me consider the right-hand side in orange. So that's pi psi p psi eta, but eta, it's a psi ch x. So a psi ch x, it's t x a psi. So this is t x a psi, because at y it coincides with psi, and at x it's equal to a. So this is eta. Now, by this definition, this is equal to psi pi psi, then 1 over v, then pi psi x a. And this is pi psi divided by v. And this, by this formula, it's pi a psi ch x divided by the sum. But a psi x ch, it's eta. So this is eta, and I get exactly the formula I wanted. Psi pi psi pi eta divided by v divided by the sum. This is exactly. So this is proved. And it shows, therefore, that this dynamics is invariant or reversible with respect to this measure. So if we are able to prove in our model that the chain is irreducible, we can use the Gibbs Sampler in order, well, to get a sample of pi. we can start our configuration, our Markov chain from any configuration, and use the theorem to say that xi n, the distribution of xi n, will converge to pi. So this provided we prove that the chain is irreducible, and that's model dependent. So for each model, you have to show that it is irreducible. We have shown it in the case of the hard-code model. As I said, in the case of the Q coloring, that might be a difficult problem. But in any case, if in your model you are able to prove that it's irreducible, you know that as n, well, for n very large, the distribution of xn will be close to pi. But we have to quantify how close xn will be is from pi. So that we will, this is the, well, one main concern. How can we quantify this, this distance? And so maybe before I proceed, let me just show that indeed in the hard-code model, the algorithm we proposed, it exactly corresponds to the Gibbs Sampler. So let me conclude this lecture by showing that indeed the algorithm we proposed is the Gibbs Sampler. So here's the formula for the Gibbs Sampler, where pi is given by this expression. And so now let's take in our example, S would be 0, 1, and omega, the space of configuration in which two sides are not occupied at the same time by a particle. So in that case, what is pi x eta of A? Well, there are two possibilities. Either x belongs to the set V eta. So remember that V eta is the set of vertices such that eta z it's equal to 0 for all neighbors z of y. So it's the set of vertices y such that all neighbors of y are empty. So y can take two values, 1 and 0. So if x belongs to v of eta, this means that the value of x can be either 0 or 1. And so this pi of x will be pi a eta x ch divided by pi 0 eta x ch plus pi 1 eta ch. Right? Because, well, there are only two possible values for each spin, either 0 or 1. So this sum, it's a sum over two terms, and these are the two terms. And since pi is the uniform measure, this is equal to 1 over 2. And of course, I forgot here 1 over v in my formula. And so this quantity, if x belongs to v of et, it's 1 over 2. If x does not belong to v of eta, so if there is a neighbor of x which is occupied, then the probability that you have a 1 at site x, that this is forbidden, because this configuration is forbidden, doesn't belong, so this configuration does not belong to the configuration, and therefore what we have here is p. So what I'm claiming is that if this px of eta 0, it's equal to 1. This is the only possible value. Px of 1, it's equal to 0. So if I translate this formula, what I get is the following, that p eta tx a of eta, it's equal, well, here I have to divide x in two cases. Either x belongs to v of eta. If x belongs to v of eta, we have seen that this probability, it's equal to 1/2 whatever a is. So this is equal to 1 over 2v. for a equal 0 or 1, while if x does not belong to v of eta, this is equal, well, 1 over v. And here we need a equal to 0. And actually, t x a of eta, in this case, it is tx 0 of eta, and this is eta, right? Because since eta, assuming that eta belongs to the configuration space, omega, and since x does not belong to v of eta, means that there is one neighborhood of x which is occupied. This means that eta x must be 0. So that tx0 is actually equal to eta. So what we get is that p eta tx will have two different values. If x belongs to v, it's 1 over 2v. If x does not belong to v, then, well, this probability is just 1. And from that, we get exactly the same formulas that we have. Let me rewrite. So remember that we denoted by sigma x of eta the configuration at which I flip the site at x. This means that p eta sigma x of eta, well, if x belongs to Vn, to V of eta, this is what I get. So that will be if eta x is equal to 0, that will be to take a equal to 1. If eta x is equal to 1, it would be to take equal to a equal to 0. But in both cases, this is 1 over 2v. So the probability that you jump from eta to sigma x, it's 1 over 2v if x belongs to v of eta. And, well, to get, remember, and this is the only case, only configurations to which you are allowed to jump. All the other configurations, so p eta xi will be equal to 0 if the distance from eta x is larger than 2. If the distance from eta to xi is equal to 1, then we are in one of these cases. But we have seen that in the hard-coded model, if x does not belong, then you are not allowed to flip. So that probability will be 0. And so these are all possible jumps. So I hope it's clear. So what I'm proving here is that indeed the hard-coded Markov chain we constructed corresponds to the Gibbs Sampler. We have here the formula for the Gibbs Sampler. Now if we recall that omega has, that S has only two values, 0 and 1, we can get this explicit formula. But now we have a different value, either for x not in V and x in V of eta. For x not in V, what we get is that these probabilities are equal to 1/2, while if x is not in V, these probabilities are 1, but puts weight 1 at the value 0. So that gives me a further contribution to the probability that you jump from eta to eta, because you're not allowed to put a particle. So the only configurations, what I'm claiming, what I'm making a point here, is that the only configurations in the hard-coded model for the Gibbs sampler, if pi eta xi, if I take a xi different from eta, and if pi xi of eta xi is positive, then xi it's equal to sigma x of eta for x in V of eta. This is my claim. This is what I'm trying to convince you, that if pi p of eta xi is positive and xi is different from eta, this means that psi is equal to sigma x eta for x in v of eta. And moreover, this probability, in that case, this probability is equal to 1 over 2v. So let me prove this claim. Here is this probability. So I'm assuming that psi is different from eta. So if psi, so let me erase and to make this claim, the proof of this claim clear. So I'm taking psi different from eta. If psi is different from eta, and if the probability of jumping is positive, this means that the distance of eta to psi has to be equal to 1. It cannot be larger or equal than 2 because the probability of jumping to a configuration with distance 2 is 0. And here I'm assuming that the probability is positive. And it cannot be 0 because I'm assuming that psi is different from 0. So the distance has to be 1. Since the distance is 1, this means that psi is equal to some t x a of eta, where a it's equal to 1 minus eta x. So actually, psi is equal to tx 1 minus eta x eta. Right? Because I want it to be different, the values at the spins are either 0 or 1. So if I want psi at x to be different at eta at x, it has to be 1 minus eta x. So this is psi. Now, this means that psi it's equal to sigma x eta. So this is what I'm claiming here. Psi it's equal to sigma x eta, right? So let me repeat. The distance is 1. So if the distance is 1, this means that they differ at one point. So this means that psi it's equal to eta everywhere but at one side. And since they are only 0 and 1, this means that psi has to be equal to eta where you flip the site x, the configuration eta at x. So that means that psi is equal to sigma x. So here I just prove this claim. Now I have to show that psi is actually in v of eta. Well, that x is in v of eta. Well, if x it's not in v of eta, this means that if I take x, so there is a neighbor of x, say y, in which I have a particle. And therefore, I cannot have a particle at x, and therefore x has to be in v of eta. Because if x is not in v of eta, psi, which is sigma x of eta, does not belong to omega. So I need x to be. So that proves that x belongs to v of eta. And my final claim is that this probability of jumping is 2v. So let's prove that. Well, so what is the probability that I jump from eta to psi? Well, but the psi, I reached the conclusion that psi is equal to txa eta, and that x belongs to Vn. Now I can go to this formula. This tells me that this is 1 over v, pi x eta of a, and now pi x e of a, it's equal to 1/2 if, here I erased, but if x belongs to v of eta. So if x belongs to v of eta, this probability is 1/2, and so this is equal to 1 over 2v. So we just proved that in the case of the hard-code model, this claim, so that if the probability of eta psi is positive, psi different from eta, then psi is equal to sigma x of eta for x in v of eta, and the probability eta psi it's equal to 1 over 2v. Therefore, I'm allowed to write pi eta tx sigma x eta, that this is equal to 1 over 2v for x in v of eta. So these are the only allowed configurations which are different from eta, and pi eta eta, it's equal to 1 minus the probability, all these probabilities, but this is the number of sites here, v eta divided by 2v, and pi eta psi, it's equal to 0 otherwise. And this is exactly the definition of the Markov chain in the case of the hard-coded model which I proposed. So the dynamics I proposed, it's actually an example or a particular case of the Gibbs Sampler. So the Gibbs Sampler, it's a general strategy in order to define Markov chains which are reversible with respect to a measure pi. And we can use this Gibbs Sampler in order to construct samples or in order to construct distributions of configurations. So I'll stop this lecture here. So what did we do? I proposed a problem to construct samples out of uniform distributions, and I propose a strategy which consists to follow to construct this Markov chain through this Gibbs sampler to prove that this Markov chain is irreducible, then to run this Markov chain up to a very large time, at which point we will have a configuration whose distribution is very close to the stationary distribution. So there are two open questions which I need to answer in the next lecture: how to construct a Markov chain through this uniform distribution, and then we have to start discussing how fast you converge to the distribution, to the stationary distribution. We need to provide bounds, explicit bounds, on the distance between the distribution at time n and the limiting distribution, the stationary distribution. And this will be the main topic of the next lectures.